Okay, so today we're going to start talking about how we measure concentration per solution. So sometimes you want a chemical that's stronger, and sometimes that you want it weaker. So we know a lot of things are solutions, and we're mixing them with water or some other solvent. And sometimes you need something very strong, so that would be a high molarity or a high molality. Sometimes you want ones that are fairly weak. So when you're doing a lab, a lot of times you've noticed it said like 3.0 mHCl or 6.0 mHCl. So the higher the number, the more concentrated. A couple vocab terms you're going to need to know for this. So the whole thing together is called a solution. It's made up of a solute, which is the substance present in the smaller amount, and that's usually a solid, so like a powder like NaCl or KBr. The solvent is the substance present in the larger amount, so most cases it's in a liquid, and it's usually water. Water is known as the universal solvent because they use it in so many solutions, and it mixes with a lot of the chemicals we use on here. So again, the whole thing's the solution. What you're mixing into the solvent is called the solute. The solvent is usually water, but it could be something like alcohol that they mix with instead. Okay, so there's two equations and they sound very similar, so we got to watch out about which one's what. The first one, the one we'll use more often, is called molarity, and the equation for that is moles of solute over liters of solution. Now molality is very similar. It's our moles of solute as well on top, but notice it's kilograms on the bottom, and it's not solution, it's solvent. So realize when you're adding something to solvent, you usually have more solution on there. So I might only use 800 milliliters of solvent, but once I put my other stuff in, it might go up to 900. So that's kind of going to be the little bit of the difference between these two. Molarity is a capital M, molality is a small cursive M. Okay, so let's start with something basic, so the molarity equation. So again, what I'm going to be using for this is molarity is moles per liter. And let's just start off with a basic problem here. We have 11.0 moles of KOH, and we're making 2.0 liters of solution. What's the molarity? So you want to check first, make sure it's in moles, which it is. If not, you're going to have to convert grams to moles, or they might ask you in a problem to solve for moles and put it in grams. So we're just going to take 11.0 and divide it by 2.0. I keep my least amount of sig figs, which is 2. So my answer here would be 5.5, and again, capital M, which is pronounced molar when we say that on here. So my solution is 5.5 molar. Okay, now this one we're going to have to do a little bit more work for, because notice this is in milliliters. So the first thing you need to do is move that back 3 spots. And then we know the molarity here, and we are asked for grams. So again, we need to find moles before we can find grams, and then we'll use the molar mass to finish this up. So the first thing I need to do is either plug it in as is. So if I do that, molarity 3.00 is equal to our moles, which we don't know, so we can just put X or X moles. And then we know it's 0.475 for my liters. So this is something I have to do often because I have to make up your chemicals for the lab. I add up how much each of the groups need. I know the strength. I have to go to the balance and figure out what I need to actually get how many grams. Okay, so that would be your first option, is to set it up as is. If you want to solve for it and figure out where the moles would be in the equation, if molarity is moles per liter, then that means that moles is going to be molarity times liters if you rearrange this and multiply both sides by liters. So either way is fine. You're going to end up doing the same thing in your calculator. So it's going to be 3.00 times 0.475. So I'm going to take 3 in my calculator times 0.475, and I'm allowed to keep 3 numbers on here, so least sig figs. And so I get 1.425. I'm going to go ahead and round that off to 1.43 moles. And then you'll need to go ahead and find the molar mass. So Na and Cl together, a lot of you probably have this one memorized by now, we use it so often, is 58.44 grams per mole. And once again, I'm going to keep 3 sig figs in my answer. And so I get 83.5692, so I'm going to round this off. to 83.6 grams of NaCl. Okay, so that means if I'm going to make this, I need approximately 83.6 grams. So we're rounding it off a little bit on there to get to know that we might be a little bit off. We just have to be within a couple, a little bit of that molarity. Okay, so 83.6 is what I would want to go get on the balance to do this. Myself on there by dividing the moles by the liters, and I should get the molarity in my solution. If not, you know, there's a little bit of a problem. Okay, so in this one, we're now going to find molality. So remember that molality is the moles over the kilogram solvent on here. Okay, so 4.3 is my moles, 3.5 are my kilograms of solvent. So I've got two numbers in each of these. So I'm going to keep 2 sig figs on here. So this would be 1.2, and I'm going to label this with the cursive M, and it's kind of a hard word for some people to say, molol on there. So molality is 1.2, or you could say the molality is 1.2. Okay, so again, just watch where they are. To solve for something else, just like in the other problems. So if I want to find the kilograms on here, I can either just plug it in as usual, or if my molality is my moles over kilogram, I'm going to have to move things around, and I'll figure out that kilograms is going to be equal to moles over molality. So if I plug it in, 6.5 is equal to my moles, which is 5.4, and then I don't know my kilograms. You can just put X. You don't have to put kilograms. To solve this out, I'm going to have to take my moles, 5.4, divided by my molality, which is 6.5. I can keep two numbers, and this is 0.83. Watch your label. We are asked to find the kilograms, or about the solvent. So I'm going to need 0.83 kilograms of the solvent, which would be the water. Okay, remember for water, it has a density of 1, so 1 gram is 1 milliliter on there, so you may be asked to convert something, but however many grams of water would be the same amount of milliliters on there if they happen to give you milliliters instead. Okay, so that's molality. Okay, so we've got one other equation, and that's how to dilute a solution. So you'll notice this formula, M1V1 equals M2V2. So that looks a lot similar to Boyle's law, where you see the 1's on one side and 2's on the other side. So remember, that means it's an inverse relationship. So M is my molarity and V is my volume. So if I make my solution have a bigger volume, I'm watering it down, so that means that it's weaker. So if I have more solution, it's weaker. If I have less solution, it's stronger. So when I dilute something, I have more of it, but it's less concentrated. Similar to Boyle's law, your volume can be in milliliters or liters or on here. You just need to make sure that they match. And again, the 1's just stand for initial and the 2's stand for your final. So your 1's are your beginning, where you say this solution has this molarity and this much volume. It's being diluted to this new set of situations, and that's going to be your 2's on here. Okay, so let's look at this one. We have 250 milliliters of solution, and it is now needs to be 500 of 6. So I have to do this a lot in your lab. The chemicals come in certain molarities, and I have to water them down to get what I need. So if I need 6 molar in the lab and I need 500 milliliters, I need to be able to figure out how much to get in a different strength on here. So since it says starting, that means I'm looking for M1. So M1 times the amount that I'm starting with is 250 is equal to M2, which is 6.0, times V2, which is 500. So I'm going to put this in my calculator. Now you can notice on here I doubled the amount of solution on here, so that must mean it was originally twice as weak. So I'm going to take 6 times 500 and then divide it by 250, and then my answer on here would be 12 molar. Now if somebody puts 12.0, since that has the 10th, I'm fine with that too, but technically we're really only supposed to keep 2 on here. So if you put your solution to half as strong, you're going to make twice as much of it. And you can be asked to solve for any of those letters in here. One thing that has a little bit added step to it is when they ask you how much water is added. So you're just going to do a little extra step. So M1 here is 12, V1 is 2.5, M2 is 3.0, and we don't know V2. So we're going to go ahead and take 12 times 2.5, and then we're going to divide it by 3. And we get our answer here of 10. Okay, then we're going to go ahead on here and subtract the original amount that we had on here. Okay, now really we're only supposed to keep 2 here, but since our device on here is going to be calibrated the same, I'm going to go ahead and keep the 7.5 liters on here, because when I plug that in, that will work better. So again, kind of go off with what you have on here. This was measured to the tenths our device does, so really even though this is only 2 sig figs, I would go ahead and keep that one on this case. Again, some will just be special situations. So that's how much I would need to add. So I would take my cylinder with the 2.5 liters of HCl, and I would need to get it up to 10. Now, one safety thing on here, you're supposed to add acid, so it'd be better in here to put the 7.5 liters of water and then add the acid. It's a little bit safer to do it that way on here.